Hello, my name is Igor Shinkar, and in this video I will talk about relaxed locally decodable codes with nearly linear block length and constant query complexity. So this is based on joint works with Alessandro Chiesa, Tom Gur, and with Vahid Asadi. So the title is sort of long. So here is a shorter title that's maybe easier to read. I'm going to talk about short codes with local properties. Okay. So I will start with standard notions of error correcting codes, and then I'll tell you what I mean by codes with local properties. So what's the standard setting of error correcting codes? So we have some message M, and we would like to, encode it using some encoding scheme that we call C. So C gets a message and outputs a longer string. And then we store this encoding on some disk. And we say that this, I will tell you why we're storing it on disk. So we say an encoding has a good distance, it has distance delta, if for any two messages, their encodings differ in at least delta fraction of coordinates. So even if the two messages differ in only one coordinate, for example, it doesn't matter. The encodings differ in many coordinates. Why is this useful? So suppose some part of the encoding has been corrupted for some reason. We can still recover the message. Specifically, if the number of corrupted coordinates in the encoding is less than delta over 2 times n, then just information theoretically for this point, there is exactly one code word within this radius of delta n over 2. And so the message, at least information theoretically, can be recovered. And in general, yeah, we know a lot about error correcting codes in general. We know trade-offs between what's the optimal length to distance. We know how to construct these codes explicitly, all sorts of fancy things that we know about these codes. So here's what I'm going to focus on today. So I want to talk about the problem where we don't want to decode the entire message, but want to decode only one bit of the message. Okay. So the standard notion for this is locally decodable code. So we have a local decoder. So it gets maybe an encoded message, C of n, but maybe this message is noisy. So some bits are corrupted. And we get an index I of the message. So here's what local decoder should do. It should read a small number of bits from this noisy code word and output mi, the ith bit of message with high probability. Okay, so here is a formal definition. So we have this code. So what's a code? The code is a mapping that takes k bits and outputs n bits. And we say it's locally decodable if there is a decoding procedure such that the decoding procedure takes a word W maybe it's a code word, and maybe it's only close to a code word. So it's a code word, but slightly corrupted. And it gets a coordinate I, and it makes only small number of queries to this W, to this corrupted code word, and recovers the ith bit of the message with probability at least 2/3. So there is something a bit inconvenient here that I refer to bits of the message and bits of the code word. So from now on, I'm going to assume that actually the code is systematic. What does it mean? It means that in the encoding, in the n bits of encoding, the first k bits are simply the message itself. Okay. So for this problem, if the ith bit is not corrupted, that's kind of great, right? Then we can just return the ith bit by looking only at this one bit. We don't need Q queries, but we don't really know if the ith bit is corrupted or not. So yeah, this is what makes this problem interesting. Okay, so we somehow need to check if this bit is corrupted, and if it's corrupted, then interpolate other bits to get information about the ith bit. Yeah, that's kind of in one sentence what's going on. And locally decodable codes and more generally locally correctable codes have many applications in theory. So to data storage and hardness of approximation and de-randomization and program checking. And that's all great, except that the best LDCs we have with constant query complexity are only slightly sub-exponential, which makes them sort of not very useful for applications. And a question we can ask is, can we achieve shorter code, let's say of polynomial length or even linear length, with similar local decoding properties? So to answer this question, there is this notion of relaxed locally decodable codes. So it was introduced by Ben-Sasson, Goldreich, Harsha, Sudan, and Vadan. And the observation was that for some applications, it suffices for the decoding algorithm to allow the decoding algorithm to say, I don't know, if the algorithm sees that the word is corrupted. So if the algorithm, this decoding algorithm detects somehow that, oh, there is some inconsistency here. You know, I'm reading qubits and they don't look like restriction of some code word. You can just say, I don't know. Okay, it just can output bottom and it doesn't have to return the correct symbol. And it seems like, yeah, what's the big deal? But it turns out that it was actually quite useful in the sense that it allowed us to construct much shorter codes. So here is the picture now about relaxed locally decodable codes. So as before, we have a local decoder and gets a noisy code where it gets an index, makes few queries, and now it needs to output either MI or it needs to output bottom. So bottom will say, yeah, I found an error, I don't know. So to make sure that the local decoder doesn't output bottom all the time, we put a restriction on it. So the restriction is if W is really encoding of some message, if W is really a code word, then the decoder must output the correct value. It must output the ith bit of the message. And the robust property of this is that if W is close to encoding of some message, tau close, then decoder must output either MI or it can say, I see something is wrong, I just don't say anything. Okay, it can just reject. And it must happen with high probability. That's the definition of locally decodable codes. Yeah, and the decoder makes at most Q queries to W. So that's the definition of locally decodable codes. Here is our main theorem. So this is a joint work with Vahid Asadi, and it's relying on previous work with Alessandro Chiesa and Tom Gur. And the theorem says the following, that for all epsilon, there exists a relaxed locally decodable code whose length is n, which is equal k to the power 1 plus epsilon, and query complexity is order 1 over epsilon. So the length means that the code takes k bits of message and encodes it using k to the power 1 plus epsilon, 1.1 bits of the code word. And the dependence between query complexity and the length is this epsilon. Okay, so if the length is k to the power 1 plus epsilon, then query complexity is order 1 over epsilon. So that's certainly much better than what we can get with LDCs, but it just shows it's a different object. Okay, that's what it really shows. So to compare it to previous work, I think I'm going to compare it only to this work of BJHSV, who showed a construction of these RLDCs, relaxed locally decodable codes, where if we fix the same epsilon and let n be k to the power 1 over k to the power 1 plus epsilon, then the query complexity is 1 over epsilon squared. While our work gives a different construction where the query complexity is only 1 over epsilon. And I would like to also mention the lower bound. So the lower bound is a work of Tom Guran and Oded Lahish. And they showed that query complexity for such length must be at least square root of 1 over epsilon. So we make partial progress toward closing this gap between what's the upper bound and what's the lower bound. So previously the gap was, I suppose, power 4, and now the power is only 2. That's the main result. And what I'm going to show next is some ideas that go into the proof of the theorem. Okay, so from now on, I will tell you about the proof of the theorem. All right, so remember this picture. And remember definition of relaxed locally decodable codes. So I'm going to make a simplifying assumption. And the simplifying assumption will be the following. Let's say decoder reads some Q coordinates of W. And if these Q coordinates are consistent with some legal code word, then it just outputs WI. Okay, so here I'm assuming that the first K bits of W are supposed to be just the message. So outputting WI is right. If WI is correct, then we just output WI, and otherwise we, if we see some inconsistency, then we take the easy way out. And we say, oh, I found inconsistency, so I don't play this game anymore. I reject. Okay, and if we see no inconsistencies, then we just return the ith bit of the word. So this is this simplifying assumption. This is what we're actually going to do. And if you want to compare it to the locally decodable codes, to not the relaxed definition, to the standard definition, then this is a huge difference, right? Because in locally decodable codes, we're not allowed to output just the bit that we see. Okay, so we're going to make this assumption. So before going into this k to the power 1 plus epsilon, let me show you a proof sketch where n, the length of the encoding, is k squared. Okay, so it will be only k squared, but it will show kind of the first idea. So here's what we do. We start with the code of bivariate polynomials G, so over some field. So think of the field size as 10 times the degree. So it means we're encoding roughly d squared symbols into f squared symbols, right? D squared symbols of the message into d squared symbols of the code word. And how would we decode the value of a particular coordinate? So here's an idea. Here is step 1. We're going to read the entire row containing this this coordinate, right? This value, that this cell that we want to decode. So that's the first thing. So there's nothing random here. Just choose one row. Just choose the row. And for the column, we're going to choose a random column. This is our randomness. So we choose a random column. And what do? We check that the row has degree at most d, and we check that the column has degree at most d. If both have degree d, if both are low degree, and well, we also check consistency on the intersection. Okay, if we read the entire row and the entire column, then of course they are consistent on their intersection. Then we just return the value in the query that we want, right? In this position 3, 3. And if either the row or the column are not polynomials of degree d, then we're just going to reject. So our decoding procedure makes 2 times square root n many queries. Right? So we have square root n many queries for the row, square root n for the columns. Maybe there's -1 there. And here is a small claim, not very complicated. If W that we get is, let's say, 1% close to some polynomial, but the value in this position that we want to decode is incorrect, then the decoder will reject with some constant probability. And to see the proof of this, let's say that this closed polynomial is just the zero polynomial, okay? So it means that most entries in this matrix are zero, but specifically in this position, the entry is not zero. Then, well, what happens then? If we look at the row, if we want this to be a polynomial of low degree, there must be many non-zero in this row. Then if we choose a random column, it must also hit, well, with constant probability, it will hit some coordinate, will be non-zero. On the other hand, if we know that the entire matrix is close to zero, then these things can't live together. So it's impossible that each column, that most columns are close to zero, and on the other hand, most columns have non-zero in this special row, in the third row. That's kind of a claim of this proof. So in fact, so far we don't get constant number of queries. We get square root n queries. To reduce the number of queries, we need a robust version of this. So the robust version of this says the following. Let's again make this assumption that we're close to some polynomial, some polynomial g, right? So g is the right polynomial, but in this value but in this point, the value is incorrect. Why are we making this assumption? We said we always either return, I don't know, or we return the value in this point. So if the value in this point is correct, then the decoder just succeeds always. Okay, so we assume that the value in this point is incorrect. Okay, so we're close to some polynomial g, 1% close, but the value in this point is incorrect. Then here is a claim. Either this row must be far from a degree d polynomial, or if we choose a random column, then a random column with high probability will be far from a low degree polynomial. And actually, this claim is almost true. And when I say almost true, well, in general, it's not true. Why is it not true? Because, for example, you can take W to be all zeros and put only W in this position 3, 3 to be 1, let's say. So it's very close to the zero polynomial, but it's not true that either the row or one of the columns are far from low degree polynomial, right? All of them are close to zero. But if we define the appropriate notion of far, so what's an appropriate notion of far? We should give weight to this point that we're looking for. So let's say with probability 1/2, we check that the value is consistent with the value in this specific point is consistent with the global polynomial, then things work out. So we need to define the notion of far appropriately, and then things work out. But basically, this is the robust version of the previous claim. So again, if W is close to some polynomial, let's say to the zero polynomial, but in the point that we want to decode, the value is wrong, then either the row is far, or a random column will be far with constant probability. Okay. And far is this notion that I'm hiding from you. All right. So what do we have so far? So far, the number of queries is 2 times square root n. The length is, well, it's order k, right? Because we encode d squared using f squared symbols, and k is d squared, and yeah, so n is basically 100 times k. And we have this robust rejection probability. And why is it good to have robust rejection probability? Because if we have good robust rejection probability, then we can use the so-called PCPs of proximity. And these PCPs of proximity are these objects claiming or certifying that the view in each row is close to this univariate low degree polynomial. So what we're going to add to the actual construction is not only the polynomial encoding, but also we're going to append to it a bunch of proofs of proximity. How many? Well, for now, let's say one for each row. And what will these proofs of proximity do? They certify that the row really contains a low degree polynomial. And again, I'm slightly cheating, and I'm cheating exactly because of the same reason as before. We don't have proof for each row only, but the proof is for each point and the line containing this point. So for each point, we have this line and this line. And the proof certifies that the restriction to this line is low degree polynomial, and the point, in fact, agrees with this low degree polynomial. Okay, so it's a stronger assumption. Okay, so first of all, the line is a low degree polynomial or close to a low degree polynomial. That's one. And two, this point, so for each point separately, this point agrees with this specific low degree polynomial. And it's possible to write such PCVBs. So what's the length of each proof? So the length of each proof is almost linear in F. And the total length, so for each point, we have something like, how many points do we have? We have F squared many points. For each point, we have 2 lines, so that's another times 2. And then we multiply by the proof length. And the total length becomes something like K squared. I will skip the exact computation, but that's but that roughly covers that's roughly the idea. All right, so that's the bivariate example. So what's for query complexity? What do we do? So for query complexity, instead of reading the line, what we will do, we invoke this PCP of proximity once for the row and once for the column. And the PCP of proximity will make constant number of queries for the row, constant number of queries for the column. So the total number of queries will be some constant. Okay, so the total number of queries is constant and the length is roughly K squared. Okay, so just to repeat, as a first step, we read the entire row and a random column. And then we say, oh, that's too many queries. No, let's pay a bit in the length. What do we pay in the length? In the length, we pay by adding all these proofs of proximity. And then instead of reading the entire line, all we need is to use the proof of proximity to check that this line is really close to low degree. Okay. That's when n is K squared. So dimension is 2. So how would we generalize it to? So next what I'll do is show how to generalize it to higher dimensions, and higher dimension will allow the length to go to be K to the power 1 plus epsilon. Okay, so here's what we do. We encode a message of length K using Reed-Muller code of dimension M that's roughly 1 over epsilon. And I cannot, well, I cannot draw an m-dimensional cube, but I can draw a 3-dimensional cube. So we'll pretend that this is an m-dimensional cube. So let's say we want to decode this value. So here's what decoder is going to do. It's going to read the line. Then it's going to read a random, right? So first it reads a random row. Then it's going to read a random column. And then there is a 3rd dimension. Now it's going to read a random 3rd dimension. Okay, so it happened to choose the top row. So it could choose any other row intersecting this column. So it chose the top one because this one we can see. All right. So in addition, Right, and what is the what's the decoder doing? What is the decoder supposed to do? It expects to be this line to be low degree, this line to be low degree, right? The row to be low degree, the column to be low degree, and this line to also be low degree. And in addition, again, we have for each line and point, we have a proof claiming that the line is close to low degree polynomial and the point is consistent with this low degree polynomial. Right, so every intersection point, we ask for the intersection point to be consistent with the next line. So what's really going on is what we do is we do basically a random walk using these constraints. So we start with some point x0. So this is the point we want to decode. And we want to run this consistency test. So what's a consistency test? So it's consistency test using random walks. So we choose one line and we choose the other line, and each next line intersects the previous line. And we check that all lines are consistent with some low degree polynomial. And if all of them are consistent, then we say, well, it looks like a correct code word. So what we're going to return is just the value in this point x0. And if one of the lines doesn't look like a low degree polynomial, then we're going to say, haha, we caught an error, something is wrong, and then we return reject. And instead of reading the entire line, so reading the entire line is expensive, right? So we would pay, if m is the dimension, we would read something like f times m many points. That's too many. Instead, what we're going to do is we're going to have PCPPs for each line in each direction, right? So we're going to see, we're going to have this proof of proximity for every line, horizontal line, vertical line, and line depth. And instead of reading the entire line, we're going to use only the PCPPs to check the proofs. And the guarantee is the following. If we have this CTRW, so CTRW is consistency test using random walk, starting from x0, and if our input is close to some low degree polynomial, but it's wrong in the starting point, then there is some probability that one of the lines will be far from any low degree polynomial. And if it's far from low degree polynomial, then the PCPPs are going to catch this and we're going to reject. Okay, so the guarantee, if the value in the point x0 agrees with the G on x0, then we're fine. And if they don't agree, then this random walk is going to catch this with some probability. Okay, so think for now it's going to reject it with constant probability. So working out the parameters, the dimension will be roughly 1 over epsilon. That's what we need for this setting if we want n to be k to the 1 plus epsilon. And the number of queries will be, so let's see, we make m steps in the random walk. So we first choose in the first direction, then the second direction, then the third direction, and so on. And on each such direction, on each line, we don't read the entire line, but rather we read the PCPPs only, right? We invoke the PCP machinery. So it only takes order 1 over epsilon queries. So it's m times some constant number of queries, so we get O of 1 over epsilon. And the total length, I will skip it, but it basically works out. It works out almost fine, except that when running this CTRW, the probability of catching inconsistency is only theta of epsilon. So it's really small. It means that we need to repeat the procedure 1 over epsilon many times, and hence the total query complexity is not 1 over epsilon as we want it, but rather it's 1 over epsilon squared. Okay, so we're almost there, except that so the length is k to the 1 plus epsilon, but the number of queries is 1 over epsilon squared. And this construction matches the parameter of BJHSV, although the construction is a bit different. Okay, then then here's what happened then. Then came this guy Vahid. And he said, yeah, it's all nice, but we can slightly improve it. And what I'm going to show next is how to improve the query complexity to only 1 over epsilon and not 1 over epsilon squared. So in order to obtain these RLDCs with query complexity 1 over epsilon, here's what we're going to do. We're going to perform a random walk, not using lines, but using planes. So we choose one plane containing this point. Then we're going to choose a line. Then we're going to choose another plane crossing this line so that 2 consecutive planes intersect on the line now. So previously we had one line and then another line, so they intersected in a point. Now we're going to choose planes that intersect on lines. And you may think, yeah, what's the big deal? But in fact, we're going to use not only axis parallel planes, but we're going to use planes in arbitrary directions. So here are some facts. So if we use only axis parallel planes, then the length of the walk will really not change. So the query complexity will stay about the same. If we use all planes, then it's too many planes, right? So all planes, remember, for each plane, we want to have a proof of proximity. And if you do the arithmetics, then all these planes together, there's too many of them. So the PCPPs, only the PCPP parts of the encoding will be just too long. Okay, so each PCPP is maybe short, but there's too many of them, so it will be long. So we'll use only planes of the following form. So we start with some point x, and we choose a plane where, so we have a point x, and we have 2 vectors, h and h prime, and we choose h only from a carefully chosen subfield of f. So this is some sort of de-randomization, okay? So don't use all planes, but use only some of the planes. So we start with a point x0, we choose one plane, then we choose a line, then we choose another plane crossing this line. Then from that plane, we choose another plane crossing this line, and so on. And I will not provide more details about this because it will become kind of technical. But here is a fun claim that it's kind of the key claim in the argument. So let's say H is a subfield of F of dimension M. And let's say we choose random HIs. So each of them is vector. It's not a vector in F to the M, it's only a vector in H to the M. So the H's are kind of de-randomized. And then we choose T's to be random values in F. And then we make kind of a random walk. So what will be a random walk? We start with some point x0, and then we add to it plus h1 times t plus h2 times t plus h3 times t times h4 plus t times t, and so on. So it turns out that if we make m steps using this random walk, which, well, we have the planes, but they can be embedded into this kind of summation, then this sum is close to uniform. Okay. So again, if we choose just one vector in F to the M, yeah, it will be just uniform. But what we do is choose a small number of vectors H, right, H1, H2, such that each of them lives only in a small subfield. And then we multiply them by these different random t's, where t is not a vector, right? T is a constant, t is a scalar. So when we take this entire sum, this becomes close to uniform. And it turns out that this is what we really need for our consistency test random walk using planes to work. So I will not say more about this, but this is somehow one of the key claims that goes into the new proof. So just to repeat, the main theorem is there exists a relaxed locally decodable code with length k to the 1 plus epsilon, meaning we're code k bits using k to the 1 plus epsilon bits, and query complexity of 1 over epsilon. And this improves the previous construction of BJHSV that had the same length, but query complexity was square of this. And yeah, it's a nice open problem to close the gap between the lower bound and the upper bound. All right. And in the next video, Tom will tell you about the lower bound. Okay, so stay tuned. Thank you for now.